Okay, thank you. So, hello everyone. For those of you who were present yesterday for the presentation, I do apologize. There was a scheduling mix-up, but we are here now. Thank you very much for joining this talk. Today, we are going to be talking about how to go from a RISC-V core to a RISC-V SoC. All right. So I understand that most people will know this already, but I'll spend a few seconds establishing a baseline. The important thing I'd like to highlight is that there is a hierarchical sequence here. Okay, so lots of RISC-V cores exist. These are the blue CPU itself. If we add a few other components to the CPU core, such as a DDR controller, the interrupt controller, interconnect, SPI, I2C, etc., other things, these form together to form the system on chip. Okay, so and if we get this system on chip and add some more components, such as a clock crystal, the power supply, memory chips, sensors, buttons, etc., these components all come together to form a board or a development kit or an embedded system or a product, whichever, it depends. All right. So now let's talk about the challenge that we are trying to address here. The RISC-V ecosystem is amazing when it comes to openly available code and designs. There are lots of CPU core designs openly available. However, I mean, generally, a CPU core itself will also come with a reference system on chip design. For example, it's like, okay, here's the core, here's the Verilog source code of the core, here's the Verilog source code of a reference system on chip. And then most of the material is centered around specific aspects of the core. Oh, this core has a cache like this core has a ALU like that. So most of the material is around that core itself, which is great. There's no doubt about it. However, there's less material about how the core, the system on chip was created from scratch. Like the process of how this system on chip was made, all these wires, everything was connected. How how did this happen? It's a bit vague, or it's not. There's not enough material out there about it, particularly when it comes to teaching this area, because this is SoC design is important stuff as well. All right. So what is RVfpga SoC? This is our solution for this particular challenge. So it's a set of teaching materials. We take a CPU, the Swerve EH1 by Western Digital. It's an industrial CPU being used out in the field everywhere. We take a reference SoC, the Swerve Wolf. Okay, we take a board, a popular board, the Digilent Nexus A7, and a simulator, Verilator. All right. So the CPU, the SoC, the simulator, all the source code is readily available, and the board is quite readily available as well. Okay, and the set of teaching materials uses these as a reference, but the the, the material taught is kind of can be, there are components you can move things around. Okay. So what does RVfpga SoC include? It includes a set of 5 extensive labs. They're quite detailed, and I'll go one by one into each lab and talk about it a bit more in depth. It starts with the lab 1 introduction. Then we run bare metal software on the SoC. Then we introduce another way of making SoC using comparing Swerwolf and Fuse SoC. We talk about how to run Zephyr, a real-time operating system on Swerwolf, and we also go all the way up to TensorFlow Lite on Swerwolf. So I'll just re-emphasize the hierarchical nature that we're not specifically focusing in depth in one CPU core in one cache. We're trying to look at the whole system and trying to look at how the whole system got together, and particularly around how the whole SoC was built as well. All right. So to go a little bit in depth in lab one is a key main lab one. Most of the time was spent on lab one. We walk through connecting the CPU core, adding the clock, adding the reset, adding the interconnect, adding boot ROM, GPIO, many other components. It's very, very detailed. We go step by step, one wire at a time. So I have the lab open here. If I scroll down just little bit. Uh, Okay, so after setting the project, we start with the wiring part. So we specifically start one wire at a time. Okay, connect this AXI read address bus, connect this AXI bus, connect the clock, connect the AXI ready. There are high quality PDF versions. You can zoom into the SoC as well, but connect these pins from the load store unit, connect these pins from the interconnect wrapper. So it just goes very detailed and goes in very much depth without any excuse. So this is the final result. You start with just the core on the left and one wire at a time. After a few hours, you'll end up with a full block design SoC. It's done in a visual way so that the teaching aspect is easier and clear. All right. So now to switch to lab two, the first lab was more around the hardware, RTL, the Verilog, and how we're trying to build the Verilog side of the system on chip. Now generally we run software on the system on chip, and software written in C code. It's not necessary. There are other ways of designing RTL as well. However, in the SoC case, we lab two shows uh, how to run software on the SoC that we just made, both in simulation and in on the Nexus A7. So you don't need the physical board to go through lab one at all, and you don't need the physical board to go through lab two either, because you could use the simulator to see where exactly is the instruction, where did it reach? Did it reach the AXI bus? Did it reach this bus? Okay, it's reached here. The instruction comes back, and now it's executing. All right. So Lab 2 focuses on running bare metal software on RVfpga SoC. So now Lab 3 shows a second different approach to SoC design. The visual block design approach, one wire at a time, is great for learning and educational purposes. So one of our early beta testers, a university student, was like, there are a lot of wires in an SoC, and that's true. There are a lot of wires in SoC, and if you make it one wire at a time, it starts becoming a bit long. But this is important work. This is done in the industry, one wire at a time. However, in the industry, designers and teams of designers will usually be working on the Verilog code, not on the visual block-based approach. They will be sharing source code in a version control system, uh, or and quite commonly they will also be using a framework or a build system to generate each IP core. They'll use some framework and system to generate the SoC as well. And then there's a lot of work spent in on the build system, because across teams there are reusable IP core components. There are generic interfaces. So let's say we have an I2C core and we want to use it across 5 different SoCs. It's not like we're going to manually wire one thing at a time. So the build system is very important. So what is Fuse SoC? Okay, Fuse SoC is an open source package manager and a set of build tools that does just this. Okay, in lab 3, it takes a description file. It's like, okay, Fuse SoC, I'd like to connect this core and this I2C IP block and this DDR controller in this way, and you describe the SoC and you ask Fuse SoC to do the hard work of connecting all the wires. And if the interfaces are compatible, if the description's done correctly, it will generate the SoC. So in lab 3, we go in depth into Fuse SoC, we compare these approaches, and then we kind of use Fuse SoC to generate the system on chip. Now, this generated system on chip is very close to the same one in lab 1, except that the lab 1 is the block design one is a bit simplified because it was already very long and there were too many wires in lab 1. So we took out a few IP cores from the lab 1 block design, the manual approach, and the Fuse SoC is easy to keep adding more IP cores. I think the UART controller was extra here, and maybe the SPI, but I forget. So now, lab 4, I'd like to focus everyone's attention on the hierarchical diagram on the right. So we started with Swerwolf. We have a SoC. We started with Swerve, okay, the core, the CPU core by Western Digital. Then we built the SoC, the system on chip. that runs on very later, or it runs on the Nexus A7 board. Uh, but wherever there is an SoC, there is some software running on it. And Lab 2 was focused on just the bare metal software. But generally speaking, most real world applications will be using a real time operating system. Zephyr is an open source real time operating system. And in Lab 4, we specifically show how to run Zephyr on Swerve. Just to reiterate the hierarchy, a lot of things exist out there in one specific area. It's like, here's a CPU core, its cache is amazing. This is what we did in the cache. Here's a X, this is what we changed, and it's amazing. Now we're trying to go more wide to kind of teach more, definitely more about the SoC design aspects, but also go very wide. I was like, does a CPU core run RTOS? It's specifically when it comes to teaching in extensive labs. Okay, so moving on a bit to the lab 5. Okay, TensorFlow for as a machine learning framework, it's extremely popular, and it does TensorFlow Lite runs on microcontrollers. But for example, if you go to TensorFlow Lite, and it'll show you that, okay, this is a microcontroller, and it runs on ABC microcontrollers. But the microcontrollers are physical boards out there. But how were the microcontrollers made? What if we want the whole stack to be open source? Okay, so we take things to another level in Lab 5 by running TensorFlow, the Hello World, just the Hello World example. Uh, Again, on the figure on the right shows, we started with the Swerve CPU core. We built a SoC, we ran a real-time operating system, and then we ran a very large C framework, TensorFlow Lite. It could be any other Lite, but TensorFlow Lite with machine learning is just great. So just to demonstrate the overall end-to-end picture quite well, okay? So there are actually two courses by imagination in this area, the RVfpga and RVfpga-SoC. Okay, RVfpga is the first course. This one particularly focuses on aspects inside the CPU core and the I/O. So there are some programming parts, labs 0 to lab 5, lab 6 to lab 10 focus on the I/O, labs 11 and labs till labs 20 focus specifically on the RISC-V core, the memory system, data hazard, structural hazard, lots of instructions. Okay, how does this particular instruction work? So this RVfpga focuses around inside the core and more close to the core, the I/O specifically. Okay, and the course that we were just talking about, RVfpga SoC, it focuses more around the kind of the bigger picture and the SoC aspects. And like, okay, we're gonna focus on the SoC. We're gonna focus on two ways of building the SoC: the block design way, where we connected one wire at a time manually, and the Fuse SoC way, where we used a build system and we described our system on chip, and then we kind of, okay, so generated the sources for this SoC. We also focus on the breadth, and we wanted to talk more about Zephyr, running a real-time operating system on our SoC, and then running TensorFlow Lite on the SoC. All right. So some closing remarks. It's We went from Verilog to system on chip to RTOS to TensorFlow. All the source code is visible, and this is really amazing. When I was making it, I was thinking that I wish I had this when I was in university, because in university sometimes you get this, oh, just add this block here and add this block here, and you don't really know what's inside blocks, and you're connecting wires, but you don't really know. But now the source code is all openly available, so you can actually look inside that. How does a TensorFlow Lite command, a simple TensorFlow Lite hello world, go all the way to Verilog? Okay, it executes a tensor operation, it goes into the ALU, and the ALU executes it. It goes all the way through the interconnect, it comes back, and you see it in the serial console. Okay, so we have a set of 5 labs that walk through students on how to set this up. All right. So this was a very large team effort with lots of authors and lots of sponsors and supporters. Definitely imagination was leading the charge, but the Swerve core is by Western Digital, the Nexus board is by Digiland, the whole RISC-V ecosystem is necessary. And the authors, Sarah Harris, Daniel, Hamza, Zubair, myself, Olaf. Olaf is the author of Swerve Wolf. Robert Owen was leading the overall team and the effort as well. But there are many, many associates, many testers, many helpful contributors, many. Professor David Patterson advised us a bit as well. So now, how to get the materials? They are freely available. You just head to university.imgtech.com, top right. You can just go and register. There are brochures, info sheets, teaching materials, videos. There is a support forum as well. There's definitely material in multiple languages. There's material in simplified Chinese, in English. Uh, I can't remember exactly which material. RVfpga has been translated into many languages. RVfpga-SoC is being translated or has been translated in quite a few as well. I'm not sure what's live now on the website, but all the kind of links are here as well if you want to reach out to Robert or Imagination. Uh, so now, one thing we ask, we are always looking for people who are who can be ambassadors, who can translate materials, who can keep just growing the ecosystem. For like workshop support, we do a series of workshops in many different places, and we just want to, what's it called, do more and more workshops in Japanese by the year end. We want to translate the SoC materials in Japanese as well. So if anybody is interested in assistance with that, please do reach out. I'll try and see, let me see if I can open the slide deck at the very end where you can see the helpful materials again as well. Here you go. Okay. All right. So that was it as far as the presentation goes. I'm happy to take any questions.
Thank you very much. So now I'm asking question from audience. So please submit question. So there is one question. Is there a public URL where we can browse, preview the various lab material without registering?
I don't think so. But registration, there's no major barrier or anything. If you register in a few hours, or maybe because of time zones, in a day or two later, you'll get the materials. So it's not, there's no restriction around, oh, somebody must be some great professor or anything. No, it's for everyone in academia and generally anyone working in the education space as well. There is a license to agree. I believe there are some legal implications. We can't just give everything for free. So, but the registration process is quite simple. It's not heavy.
I see. Thank you very much.
There are
Any
info
other
sheets which
question?
are publicly available. So the brochures and info sheets are public downloads. There's no need to register those. And there is
Mm-hmm.
there are research papers with further information, so you can go to and get the research paper as well, and that goes in depth, and that's publicly available as well. Both about RVfpga and RVfpga-SoC. So there's a lot of PDF downloads which are outside the registration layer. The full material, the labs themselves, and all those components, and all the getting started guide, the installation guide, which shows how to the setup Vivado, the cable drivers, VS Code, all this material itself is behind the registration layer. But the brochures, the tutorial videos, there's definitely lots of stuff. If you head to university.imgtech.com, there is a lot of material that is freely available without any registration.
Okay, thank you for your information. Yeah, so we can download that information directly from Imagination website,
Yeah,
I think.
university.imgtech.com.
Or img.com. I see.
It's this
Yeah,
one,
if we look,
university.imgtech.com.
okay. Yeah, if we look at the RISC-V international website, so yeah, there are also many educational program available now, so you can uh, find Imagination Tech educational program.
Okay. And
Yeah.
so in a bit about languages. So the SOC materials, they are in English and Korean already. And in a
Hmm.
month or so, they will be available in Japanese as well. And later on, Chinese as well, they will appear. So they are being translated. So the English and Korean are live. Next month, you'll get Japanese ones translated into
Wow.
Japanese. So, yeah. And then translated into Chinese as well.
Yeah, that's wonderful. Yeah, Japanese people, yeah, Japanese student or engineer can look at in Japanese. Wow.
Yeah.
And also, yeah, they use system Veron, right? So it's a common, yeah, very popular RTL language. And the EDA, they are using a validator or uh, yeah, many free license EDA tool. Okay, next question. Can anyone download the lab material and teaching material even if we are not in academia in as individual?
So the academics can definitely download it. When it turns to individuals, it's handled on a case by case basis. So it's hard to specify it the how do I describe it? It is more relaxed. Generally speaking, yes, everybody can access it. But if you write while registering that I will uh, change the name of everything and then publish it again as my own course, then we'll be like, okay, no need to register. But generally speaking, everybody, individuals can access it, companies can access it. If you're using the material with the imagination logo and with the material intact, it is generally it's written for teachers to teach. But if you are an individual, you can access it. If you are a company, even a commercial company, you can access it, and academics universities definitely they can access it. So just head over, register, and you'll get the download link in a bit. So it's a very kind of it's almost an open door. It's like one step away from a free download kind of sense. It's not like a restrictive or anything. Everybody can just download it. Yeah. So
Okay,
even
thank you very much.
companies like
Yeah.
Sci5 use it.
Uh-huh.
So commercial companies download and use it as well. So it's not
Oh,
an
really?
issue. Yeah, yeah, yeah.
Wow. Yeah. So maybe
So
company
if you're
can
hiring
use,
fresh graduates, yeah, if you're
yeah,
hiring fresh graduates and want to train them up in SOC quickly,
yeah,
it's like,
yes.
okay, here's a set of teaching materials. 1 week later, you have a much better fresh graduate who knows a lot about different parts of the stack, SOC design, RVfpga, TensorFlow Lite, Zephyr.
Hmm. That's good because student doesn't need to go to boot camp for such a special uh, educational. Yeah, in United States, even adult, they can go to school again. But in Japan, maybe only uh, yeah, student, no adult. Yeah, yeah. I mean,
And
it's not
next
popular.
next year,
Yeah.
yeah, for next year, we're trying to make an online course available on
Mm-hmm.
edX around our VFPGA as well. So people can then join kind of the course and get learning as well. Uh, Open to everyone, generally speaking. So, but that's something next year. So on edX as a online course and just teaching RVfpga as the whole thing, as because at the moment it's a set of teaching materials that teachers have to teach or students have to learn themselves. But with the online course, they can just like enroll into the course online and then go through as well.
Yeah, it's wonderful. Yeah. So there's no question, and thank you for your presentation and your answer. Uh,
You're welcome. And if
yeah.
there are any further follow-on questions, please reach out on any social media or the support forums or anything, and we'll happy to answer.
Oh, that's great. Thank you very much. Thank you again.
Thank you.